piece of paper, you see there's stuff on the back side. Those are not. We're just doing the front side first. We'll get to the back side today, hopefully. Ionic compounds, remember the way to identify them is metals and nonmetals. And how do you tell a metal from a nonmetal? You look at the periodic table. Remember the zigzag line. Okay, so that periodic table, if you see that you've got elements on both sides of the periodic table, ionic compound. Okay, so remember nonmetals are to the right, metals are to the left. And really, with ionic compounds, you always have a metal. With covalent, you do not. So that is really one of the big tricks is look at the first element. If it's a metal to the left of the zigzag line, then you know it's an ionic compound and you're going to have to form these charges to be able to figure out the formula. So sodium nitride. So what is the symbol? And I kind of wrote you like the steps, 1, 2, 3. You always write down the symbol. From the periodic table, you can assign the charge. With metals, their group number. And remember that the group number is up at the top. So the group number tells you the charge for the metals. The nonmetals take 8 minus the group number because they gain electrons, and that'll tell you the negative charge. So sodium is what? Symbol. It's sodium symbol. Na. And what will its charge be? +1, right? Because it's in group 1, so it's a positive 1 charge. The metal will always have a positive charge. It's the same as its group number. Also the number of valence electrons it had. And then it lost. So that's why it's positively charged. Okay? So second one, nitride. So what's the symbol? N. And when you look at the periodic table, what would its charge be? 3. Positive or negative? Negative. So be a -3. 8 minus 3 tells you, or sorry, 8 minus 5. It's in group 5A. Find nitrogen at the top of the group is that number in front of the capital A. So 8 minus 5 tells you that it's a -3. Metals always become positively charged. Non-metals always negatively charged. Metals are always written first in an ionic compound. You would never have nitrogen, then sodium. You would always have the metal written first. So remember, the metal's written first, and it's always positively charged. The non-metal's always written second, and it's always negatively charged. So see that they're not the same. So now you got to go to step 3. So if they're not exactly the same, like if they were 1 and 1, you wouldn't have to do anything. That would be the formula. But since it's a 1 and 3, what do you have to do? Do the swapping. So remember that the charge on the metal tells you how many nonmetals. So the charge on the nonmetal tells you how many metals. So how many sodium? 3. So it'd be Na3. And how many nitrogens? Just 1, because it's a positive 1. So the 1 on the sodium tells you 1 nitrogen. The 3 on the nitrogen tells you 3 sodium. That's as simple as it gets. So it's Na3N. That's the formula. So what's the next one? Calcium phosphide. Calcium is what? And what's its charge? +2. Okay? Keep the plus and the minus. Make sure that you indicate that. Don't just put a 1 or a 2 because that doesn't tell you if it's positive or negative. Phosphide, what are you going to put? What's the symbol? P. And its charge? -3. You put -3 or 3 negative, that doesn't make a difference, exactly the same. It's just telling you that that phosphorus gains 3 electrons. It has 5, gains 3 electrons to make 8. They're not the same, so now I swap. So how many calcium do I end up with? 3. And how many phosphorus? 2. The charge on the calcium tells you how many phosphorus. The charge on the phosphorus tells you how many calcium. So you just do the swapping. Lithium oxide. Did anybody coming in late? Make sure that you grabbed half a piece of paper. Lithium oxide. Lithium is, which is Li, and its charge +1. Oxygen is an O, and its charge is 2 what? -2. Include the charge. The first element's always going to be positive, and it's the group number. Second element will always be -8 minus its group number. They're not the same, so when I swap them, what's my formula? Yep, and if it's O1, you just don't put the 1, right? So if there's just 1, like NaCl, there's 1 of each, so you don't have to put the 1. Last one, magnesium iodide. So magnesium is symbol Mg. And what's its charge? It's a +2. Iodide, what is its symbol? I. And its charge would be a minus. So when I swap, what's the formula? Yep. Okay, so follow those 3 steps. First thing you do, find it on the periodic table, write its formula, assign the charge. The metal, its group number will be its positive charge. The non-metal 8 minus its group number will be its negative charge. Then, if the numbers are not exactly the same, just swap them in order to figure out the formula. When you're going to do the naming, this is way easier, right? So you just use the whole name of the metal, first part of the non-metal plus IDE. So K2S becomes what? Potassium sulfide. That's it. Potassium sulfide. And in fact, K2S, that's the only way that potassium and sulfur can combine, is 2 potassiums for 1 sulfur. Li3P, lithium phosphide. So it's phosphorus. You just take the first part of phosphorus, so it's phosp, and then add IDE. Ca3N. Whole name of the metal, first part of the non-metal plus the IDE. So you have a dynamic study module that's due Sunday night on ionic bonds. And part of it is figuring out formulas, doing the naming, going back and forth with it. So it's a good one to practice these. Now this middle part. So we talked about these. These are transition metals. And remember that I told you there's only 3 of them. It is copper, chromium, and iron. Copper, chromium, and iron, when you look on the periodic table, they are the transition metals. So they're in this area. And if you look at the top, you notice those start with a capital B for their group number. So because of this, they have lots of electrons. Their energy levels start to overlap when you start to get into these bigger and bigger atoms. And in fact, there's such overlap that these can actually exist as stable ions by losing different numbers of electrons. So for iron and chromium, iron can be a +2 or iron can be a +3. So it can either lose 2 electrons and be stable, or it can lose 3 electrons and be stable. Same thing with chromium. Chromium can exist as a +2 or a +3 ion and be stable. So those ones are both +2, +3. Copper, which is Cu, copper can exist in a +1 or a +2 state and still be stable. So when you see a formula, you have to figure out which one it is. And that's when you're trying to indicate the charge on iron, chromium, or copper, what do you have to use? That Roman numeral. So I have to have a Roman numeral. And remember that the Roman numeral indicates the charge, not the number of copper, chromium, or iron metal. It tells you what the charge on that copper, chromium, or iron is. So for example, with the name. So this is copper 2 chloride. So what's the symbol? Copper is Cu. And now that Roman numeral 2 tells me the charge is +2. Okay, the Roman numeral tells me the charge on the copper, so that is why I know that is a +2. So then chloride, what is its symbol? Cl. And so chlorine's, its charge will always be a negative, -1, because it's in group 7, so 8 minus 7 is a 1, tells me the charge on the nonmetal. They're not the same, so what do I have to do? Swap them. So how many copper do I end up with? Just 1, because that's the charge on the chlorine. 1 chlorine means one negative, 1 for chlorine means I have 1 copper. And then how many chlorine? 2, because the +2 on the copper tells me how many chlorine. It's just like before, you just swap those charges. I don't have to simplify this. This is the formula. Copper 2 chloride would be CuCl2. Iron 2 nitride. So what is the symbol for iron? Fe. And what's its charge? +2. Nitride, what is its symbol? N. And its charge? Negative what? 3. Because it's in group 5. 8 minus 5 tells me the charge. So they're not the same. So I'm going to swap. So how many iron do I end up with? Fe3. And how many nitrogen? 2. Just do these steps each time versus like jumping ahead and going, oh, I just know it's this one. Just check yourself, okay? Make sure that you write the symbol, assign the charge, swap them, and then simplify if you can. So remember, if I had a +2 and a -2, when I did the swap, I could simplify that so it would just be a 1-to-1 ratio. That's what I mean by simplify. It would only happen if you had 2 and 2 or 3 and 3. If it's 3 and 1, you can't simplify that. Or 2 and 3, you can't simplify that. It's only if they were the same, metal and non-metal, the same number of atoms. All right. It's a little more challenging when we do the next one, because the next one, you got to figure out the charge on the chromium. You just know it's Cr2s3. So again, in this, you can figure out the charge. I don't know the charge on the chromium, but I do know the charge on the sulfur. What's the charge on sulfur? It's a negative what? 2. Why? It's in group 6. Okay, so 6 plus 2 makes 8. So the -2, that's how many you're going to gain to make 8. That's the negative charge. So that's how I know this is a -2. So do you see that the chromium is a 2? The sulfur's a -2. Do you see that those are the same? The number of chromium and the charge on the sulfur is the same. So that means that the number of sulfur and the charge on the chromium is the same. It's like a reverse swap. Okay, so what is the charge on the chromium? It's +3. I don't know what happened right there. +3. Does everybody understand how you did that? So I can write it bigger. Chromium 2s3, right? That's the formula. So I know the charge on the sulfur because I can look at the periodic table. It's in group 6. So 8 minus 6 tells me that's a -2. I know that. So do you see that the chromium and sulfur on opposite sides are the same number? I have 2 chromium minus 2 for sulfur. So that means that the other ones are going to be the same as well. So the number of sulfur is 3. So the charge on the chromium is a +3. So this matches and this matches. Okay. So now that I know that, what's its name? It's chromium. 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 3. 1, 2, 3. Sulfide. That Roman, no, I don't have to put anything for this. We know sulfur. Sulfur can't be anything but a -2. So I don't need any Roman numeral for sulfur. It's only these metals. And it's just these 3, chromium, copper, and iron. Those are the only 3 that you've got to remember. There are more of them, but these are the only ones that we'll talk about again. So that's why iron exists in your red blood cells, helps to carry oxygen. We're going to talk about iron again. Copper, it's a way of detecting sugars. So we're going to talk about that again. So it's why the reason I added just these ones is because we actually will talk about them again later in the semester. So I wanted you to see why sometimes they're a +2, sometimes they're a +3. So they're sort of a special transition metal that has the ability to do that. I don't have to put anything to indicate the charge on the sulfur because the sulfur will only ever be a -2. What about the next one? So the next one, iron FeF3, FeF3, and I can write it bigger down here just so that it helps. So I don't know just off the top of my head. I know that the iron could be a +2 or a +3. Just because it has the varying charge. So if I assign the charge to the fluorine, I can figure out what the charge on the iron is. So what's the charge on fluorine? It's a -1 because it's in group 7. 8 minus 7 tells you it's a -1. So it's going to gain 1 electron, and there's 3 of them. So that means what would the charge have to be on the iron? So remember that if there's nothing, it's a 1. Do you see that these are the same? So that means these are going to have to be the same. Okay, so it's sort of this reverse swap. So if you know the formula and you make sure that that charge on the nonmetal is equal to what the metal number is, then I know that the opposites are going to be true. And 90% of the time this works perfect. Okay, so if I'm going to write it out, what's his name? Fluoride. And remember, it's fluoride. It's U-O-R, not O-U-R, because that's flour. That's just a common misspelling. And fluorine is just a capital F, not an F-L. Always. Okay? All right, so where we quit last time with the polyatomics is we talked about sort of some of these names and the charges and such. So notice with this, you might see the hydroxide written this way. What would this one's name be? Sodium hydroxide. So remember with polyatomics, that is where you have more than one atom that collectively act as the charged ion. So instead of trying to say the oxygen and the hydrogen, it's called the hydroxide. So when you see the OH written with this polyatomic form with the metal, then this is the whole name of the metal, and you just use the name of the polyatomic. So what about NH4Cl? This is the only positively charged polyatomic that we've got. You just use the name of it rather than splitting the nitrogens and hydrogens up. So this first part would be called the ammonium and chloride. First part of the nonmetal plus the IDE. What about this one? MgNO3 parentheses 2. So this one, whole name of the metal, magnesium, and then the name of the polyatomic. Now remember that it's written this way with the parentheses. You don't break up a polyatomic. So the polyatomic NO3 stays as NO3. I don't separate the nitrogens and oxygen. Think of it like it's going to behave like it's one piece. Okay? It's not going to get split up even if you have to have more than one of it. That is why you have to have parentheses. So notice in this, with magnesium nitrate, magnesium's a +2, the nitrate is a -2. So notice when you do that swapping, there would be only one magnesium but 2 nitrate ions. That is why you put the parentheses around the polyatomic. You don't ever have to put parentheses around a single element, but you do need to use it if a polyatomic is found with a number greater than 1, it's going to need those parentheses. And if you go back and look at your balancing equation sheet, all of the balancing equation ones that have parentheses, they're all carbonates, chlorates, phosphates, sulfates. They're all polyatomics. The way that they're written with those parentheses. So remember that everything inside the parentheses is found by the number outside. So now, what about this one? So potassium chlorate. So potassium is what? K. And what's its charge? +1. Because it's in group 1. It's in the first column, +1 charge. Okay? So I don't have to memorize it. I just got to remember. I look at the group number and that tells me the metal's positive charge. You do have to remember what the chlorate formula and charge. So my suggestion is you actually write these down. You write down the name, write down the formula, write down the charge. Write down the name, the formula, the charge. That you're probably going to put on your note card, okay? So that way you know what the formula is and what the charge is for those ions because they are just sort of different and distinct. I can't look at the periodic table and know what the charge on a polyatomic is. I can for metals, I can for nonmetals, but not with the polyatomics. So chlorate, I know then, is ClO3 with the negative charge. So what's the formula? Right, so see that they're +1 and -1? They're the same, so this is just like NaCl. So if the charges are exactly the same, then I know it's like a 1-to-1 for them, so it would just be KClO3. I don't have to have any parentheses. +1, becomes the number of the chlorates. -1 tells me the number of the potassium. So they're equal. Lithium carbonate. What is lithium? Li, and its charge? +1. And then the carbonate is CO3 with a -2 or 2-, means exactly the same. Either way is fine. So these are not the same, so I got to swap them. So how many lithium do I end up with? How many carbonates? 1. If I only have 1 carbonate, I don't need parentheses. Okay? I would only need parentheses if I have to have more than one of those polyatomics. Iron 3 sulfate. So what does this tell me? What's the symbol? Fe. And what's the charge? +3. And then sulfate, you can see it right there. It's SO4 -2. So now this one, I have 3 and 2. So I'm going to have to, when I swap, they're both going to end up with numbers. How many iron will I end up with? 2. Fe, 2. How many sulfates? 3. So this is where you write the sulfate, put the parentheses, and put the 3 outside. The charge on the iron tells me how many sulfate. The charge on the sulfate tells me how many iron. So I'm just swapping like I did before. But if you have a polyatomic and there's more than one, always use parentheses and then you put the number outside. I don't break it down. Ammonium phosphate. So what's ammonium? Find it at the top. It's NH4 with a plus. That's why I say like that. Those 7 are the only ones that I'll ask you. These are the most common 7. And then phosphate is PO4 with a -3. Or 3 negative. Doesn't matter. Means the same thing. Okay? So notice they're not the same. So what do I got to do? So how many NH4s do I end up with? 3. So write down the NH4, then add the parentheses, then put the 3. How many PO4s? Just 1. So that one just gets written out. I don't need parentheses on that one because there's only 1 of them. Okay, so let's practice. So do the bottom. Okay, on your half sheet, do these. Use this. So work on 1, 2, 3, 4, 5, 6, 7, 8. Okay. The first 4, you've got to go from name to formula. Second 4, you're just going from formula to name. I will flip this back so that you've got the list right there. Okay. So that you can look. These are the only polyatomics that you've got. These 7. Remember that chart that has about 15 of them? More than that. It's probably closer to 20. All right, so see how you did. So in this one, sodium nitrate. So what'd you put down first? Na and its charge +1, because it's in group 1, right? So with those that are just metals, the charge is their group number. Nitrate is NO3 and its charge is a -1, right? So here it is. There's the nitrate, so it's NO3, and its charge is like defined. It's never like, oh, maybe it's a -2 or no, it's always a -1. So that's why I say, like, in your list, write the name of the polyatomic, what its formula, and its charge, because those are all like done. Like that's what those charges are. They don't vary. Thank God. Okay, so there's this. So 1 and 1, which means what? The formula is? Yep, it's just NaNO3, 1 of each, because +1 and -1 means that I have 1 of each. So calcium phosphate. So calcium is a Ca with a +2. And then phosphate is PO4, and its charge is a -3. So with 2 and a 3, they're not equal, so I got to do the swapping. So how many calcium do I end up with? 3. So Ca3. So remember that 3 is the charge on the phosphate. And so that tells me how many phosphates? 2. The charge in the calcium tells me how many phosphates. So I have PO4, parentheses, 2. Just write the name of the polyatomic. If there's more than one, use the parentheses and put the number outside of that parentheses. Lithium sulfate, lithium is Li with the +1 charge. Sulfate is SO4 with a -2. So they're not the same, so I got to swap them. So how many lithium? Li2, how many sulfates? Just one. And if there's only one polyatomic, you don't need parentheses. Okay? Only put parentheses if I have more than one. Chromium 2 chlorate. So what does that chromium have? What's its charge? So remember, the Roman numeral tells me the charge. Doesn't tell me how many. Tells me the charge. So this makes it easier. The chlorate, what's its formula? With a negative charge. So they're not the same, so swap them. So how many chromiums? 1. So it's just Cr. How many chlorates? 2. Because the charge on the chromium tells me how many chlorates. So I write the whole formula for the polyatomic, put the parentheses, and then put the number outside is the number of those polyatomics. Okay, so those ones require a little more like, okay, I gotta do this and I gotta do that. But if, like I said, on your note card, I would definitely say those are going to need to be listed. Okay, listed, and maybe like an example of name to formula, formula to name for yourself. Okay, this is the steps. This is what I have to do to go from this one to that one. But these are the only ones. Remember when we looked at them? So here's 2, 4, 6, 8, 9, 10, 12, 14, 16, 18, 20. There's 21 polyatomics. They get like really bizarre. There's even more. This is sort of just a number. The only ones you have to worry about are the ones that you're going to see more. Okay, the ones that I chose are ones that you actually do see more in solutions. These are common salt solutions, buffer solutions that you may have to use for irrigation, that you may have to give as part of a medication. So seeing that and recognizing that a sulfate is not just a sulfur, but a sulfate is an SO4. So seeing that and not trying to grab the wrong chemical is the reason why we cover these. These bottom ones, I think they're a little bit easier just because whole name of the first element, name of the polyatomic. So the first one is what? Potassium what? Sulfate. Don't have to worry about numbers. I just have to, the whole name of the metal and then the name of the polyatomic. Don't try to split up the sulfurs and oxygens. You want to recognize that SO4 is the sulfate ion. This one's the only weirdo, okay? NH4Br, because NH4 is what? Ammonium. So NH4, you write the name of the ammonium ion goes first, and then Br would be bromide, right? Because the first part of the nonmetal plus IDE. That's the only one where it's a polyatomic with a positive charge, so it gets written first. So it kind of like acts like a metal in that one. So it's got a positive charge. So this would be bromide. BeOH2. Beryllium, 1R, 2 L's. Beryllium what? Hydroxide. So remember, you want to recognize that OH, that's a hydroxide. So don't try to name it as an oxygen, hydrogen weird thing. Just call it the hydroxide. Just keep the name of the polyatomic. Last one. Aluminum carbonate. Yep. That CO3 is the carbonate ion. So like I said, simple ions, there's like 2 ionic dynamic study modules. One is just like the top stuff. One is just getting you to do names and formulas from just metals and nonmetals. The second one is going more into some of the transition and then also more into the polyatomics, naming and practicing them. So make sure you get those done by Sunday, because that's going to help you like get this sort of more solid. I would really encourage you to try and get it done in the next couple of days, just because we've just talked about it. The sooner you do it, the fresher in your head it is, and the easier it will be to go through, and hopefully sort of like that practicing helps you go, oh, okay, I got this, all right? Just so that you know, we talk about these ionic compounds. They form these positive and negative charges. Opposites attract. That's what forms your ionic bonds. Ionic compounds are really important in the body, but they don't exist as NaCl. As soon as these ionic compounds hit water, they have the ability to separate. Just like, so if you have a cup of water, you put a teaspoon of salt in, stir it up, it disappears. Okay? It doesn't just dissolve like sugar does. It actually separates into its individual ions. So you have sodium ions. Sodium ions, this is actually the major positively charged ion that is found in your body fluids, in your blood. And in fact, it has a high effect or a major effect on water balancing. You've probably felt this effect if you've had an extremely high salt meal. So if you've gone out, one, you might go out for Chinese food, can cause this. Two, if you go out for some barbecue, it'll cause this too, because barbecue typically exists. It's barbecue that's been salted, and then you have potatoes that are salted, and then you have green beans that are salted with some hush puppies with salt. Okay, so usually that ends up being a relatively high salt intake meal. Chinese food will do this too, because what do they commonly put in Chinese food? Give some people headaches. MSG, monosodium glutamate. So Chinese food has a salt content as well. And so after you eat these kinds of things, what do you notice about your fingers, your rings, your ankles? You get swollen, okay? So you might notice your rings get kind of tight. You might notice some minor edema. That is because wherever sodium is, water hangs out too. So if you eat a lot of salt, you retain a lot of fluid. And then it doesn't have room in your blood vessels, so it gets pushed into your tissues and you end up being somewhat puffy. But over the course of 12 to 24 hours, your kidneys, as long as they're working, they're going to flush this out. But just think about sodium as being kind of this fluid balancer. This is why people that have hypertension, people that have heart disease, doctor tells them what kind of diet should you be on? A low salt diet. Right? Because low salt means you're going to hold less fluid and it's going to put less pressure on the heart and help to decrease pressure on the walls of blood vessels. So that's because sodium is a major water balancer. Calcium. Calcium is another one, but calcium, almost all the calcium in your body goes where? Into your bones. It's what makes your bones hard. Very little calcium actually circulates in your blood, but when you read through some of this, we're like, geez. But calcium is very important for blood clotting. Calcium is very important for muscle contraction and nerve conduction. Calcium is really important in a whole lot of factors, but calcium's big job is it really helps to strengthen bone and teeth. So these are some of those minor elements that we talked about, but they don't exist as a metal. They exist as ions. So sodium ions, potassium ions. Potassium. If you're low in potassium, sometimes you can end up getting what in the middle of the night? A cramp, leg cramps, okay? Muscle cramps are like commonly, can be magnesium as well, but magnesium and calcium are like kind of two big ones. And so what did your mother always tell you to do? Eat a banana. You're like, I got a cramp. Here, eat this banana. That is just because bananas are higher in potassium. Okay. So that's like another reason for it, but they're important in muscle contraction and in nerve impulses. So they say if your potassium levels are out of whack, you get these like spontaneous nerve impulses that trigger muscle contraction that doesn't stop. So that's where you get the leg cramp, because that muscle just keeps getting stimulated and stimulated. No matter how you try to stretch it out, every time you stop, your feet all go up like this, or your leg gets all tight and you're like hobbling around. I can just attest to this. This is me in the middle of the night sometimes, hobbling around. And I don't know why, but for some reason, mustard stops this. And I'm not quite sure why, because there's not like a ton of potassium, but yellow mustard, it's the grossest thing to have to be like squirting in your mouth in the middle of the night. But like if you get a muscle cramp, that is like one of the things, that and pickle juice. I don't really understand it. I don't understand it, but it's like 30 seconds after you squirt that mess in your mouth, you're like, Okay, I'm fine. Then you have to drink water because you're like, now my mouth tastes terrible. But potassium, very important in trying to help to maintain nerve impulse, okay? Because it can trigger spastic nerve impulses, which creates those muscle cramps. So these exist as these ions. I will tell you that there's negative ions as well. The chloride ion, it's there wherever sodium is, wherever potassium is, because otherwise we're not positively charged. Our positive and negative ions are equal. They're balanced. Because when you ingest ionic compounds, you ingest positive and negative ions. So they are always present, kind of like floating nearby, but they don't have to be connected, unlike the next type of bonding, covalent. HCO3, these are called bicarbonate. The bicarbonate ion is a really important ion in terms of acid-base balance. So if they talk about blood gases, and so if you have a patient that is really sick, they may check blood gases to see what is their bicarb status. Do they have a lot or a little? Because that can indicate like progression in infection. It can indicate major factors that are starting to change within the body fluids because it's very important in balancing pH. And we'll talk more about that in chapter 9 when we get up to acids and bases specifically. So there are big acids and bases that are big anions and cations or positive and negative ions that are found inside of the body that are going to come in or come back to them as we talk about the biomolecules, about carbohydrates, proteins, nucleic acids, and such. But now let's talk about the second big kind of bond. So this happens when you have nonmetals and hydrogen. These are different because, for example, here's a really easy one, hydrogen. So hydrogen, you look at the periodic table and you're like, well, hydrogen's a metal. Why is she talking about this? Hydrogen, though, is kind of like a metal, but more like a nonmetal. So one, notice it's red, which means it's a gas. In fact, most periodic tables, if they have room, they will put hydrogen like above the periodic table all by itself. If you've like searched for periodic tables on Google, a lot of them, it's not even connected to the periodic table, it's like above. And that's because hydrogen has one electron. It only needs one electron to have two, and then it's like helium. So remember I told you that those are sort of the weird ones? Those ones don't fit the mold because in the energy levels, the first energy level, very close to the nucleus and only holds two electrons. So helium's over with the noble gases because it has a full set of valence electrons with only two, and hydrogen has one and only needs one to be stable. So that really makes hydrogen more like fluorine, chlorine, bromine, and iodine, right? They have 7 and they only need 1 to have 8. While hydrogen has 1 and only needs 1 in order to have 2. So that is why hydrogen is really considered a nonmetal in terms of its desire and its pull on its electron. But if I have H2, which is how hydrogen exists, and I draw them with their Lewis dot structures, so I have this little black hydrogen, and then I'll put a little blue hydrogen across from it. So unlike sodium and chlorine, where sodium only has 1, chlorine has 7. So sodium just as soon give up its electron to the chlorine, creating the ions. With these, do you agree that one hydrogen cannot pull an electron from the other? They have like the same attraction for their electrons and also for each other's electrons. So the only way that they can actually achieve their stable group of valence electrons is to do what's called sharing. So in this, I have H2. That means that I have 2 hydrogens. I have 1 electron each, and there's 2 of them. So in order to be stable, hydrogen needs 1 bond. I need 1 bond. And if I arrange my blue hydrogen, push it a little closer to the black hydrogen, and just share the dots between them, those 2 electrons now spend 50% of their time with 1 hydrogen, 50% of their time with the other hydrogen, and that's enough to create that helium arrangement. Helium has 2 valence electrons and is stable, and so these 2 are stable with just a single pair of electrons being shared. You might draw it also with what they call the Lewis structure with just the little dashes. So I can use either the dots, but each pair of dots is equal to one of those dashes. And you've probably seen chemical bonds or chemical molecules written with dashes in the past. That's what they're talking about. If there's a dash, that's a shared pair of electrons that is not ions. So they call that a single bond. This is a single covalent bond because it is a single pair of electrons that are being shared. Chlorine does the same thing. So chlorine, which exists as Cl2, so chlorine, remember, has 7. 1, 2, 3, 4, 5, 6, 7. Right? It's in group 7, so I've got 7 dots. Remember that you never put more than 2 on any side. So 2 up, 2 down, 2 to the left, and we'll just put 1 on the right for this one. But chlorine exists as Cl2. It's called a diatomic element because it always exists in a pair. So the other chlorine, which also has 7, will need to share the extra electron. That one electron that's not paired, they get shared, placed between the 2 chlorines, and this creates the octet. So see how this chlorine now can behave as if it has 8, and this chlorine can behave as if it has 8. So when I draw the dash structure for it, there's just a single dash between the 2 chlorines, but each chlorine has 6 electrons that belong to itself. They call those 6 non-bonding electrons. They're non-bonding because they don't participate in a covalent bond. They belong to the chlorines independently. So hydrogen is only ever going to have 1 bond. Fluorine, chlorine, bromine, and iodine only ever going to have 1 bond because they have 7 and only require 8 to create that stability. So then that just leaves a couple of nonmetals that are going to need to have more than that. So looking at the periodic table, carbon, nitrogen, oxygen, phosphorus, and sulfur. Those are pretty much the only ones that aren't just going to do these single bonds. So this one kind of shows like how the 2 chlorines come together, sort of a little bit nicer looking than mine, I guess. And they call those lone pairs of electrons. I just call them non-bonding because they don't bond. They just belong to the chlorines independently. They do become important in the shape of a molecule, so that's why I make sure that I include them. And remember that the goal for everything but hydrogen is always the octet. Hydrogen, though, is only ever going to have 2. So I kind of like this. You can see the dots. And notice how these Lewis dots, how they're all spread out, like I told you to do them. So can you see that carbon's got 4 like single dots, so I know it needs 4 bonds. Nitrogen has 3 single dots, so I know it's going to have to form 3 bonds. Oxygen has 2 single dots, so I know it's going to have 2 bonds. Fluorine, though, is only ever going to have 1. So it's really just these that have the opportunity or the ability to form covalent bonds with more than one thing. So carbon. So carbon can do 4 single bonds. So a good example of this one is CH4. So from this formula, I know I have 1 carbon and 4 hydrogens. From the periodic table, I know that carbon has 4 valence electrons. In order to be stable, I need 8. So the number of electrons plus the number of bonds has to always equal 8 for everything but hydrogen. Hydrogens, on the other hand, they only ever have 1 electron and they only ever have 1 bond each. Okay? They're never going to form more than that because that makes them like helium and that's going to make them stable. So once I figure these out, I always start with, when you go to draw a covalent compound, you always start with the element that needs the most bonds. Okay? So that would be the carbon. So start with the element that needs the most bonds. That's always going to be my first step. So I place it down and I put the dots. Spread the dots out. Then I'm going to add one at a time, add the elements that needs the most bonds next, creating a covalent bond between them. So I'm just going to have like one dot from one of the atoms and one dot from the other atoms pairing up. So I add the remaining elements from the formula. And I'm always going to pair the electrons. So I'm just switch, I'll use black. So I will put a hydrogen here and pair it. I got 4 of them, so then I put a hydrogen here and pair it. I've got an empty spot up at the top. I'll put a hydrogen here and pair it. And then I'll do one more. So I'll add this last hydrogen and pair it. So just sequentially, if I have CH4, that's 1 carbon, 4 hydrogens. I have to add all the atoms, and I have to add the number of electrons that those atoms have that belong to them. But I've always got to pair them. And the rule is always just do single bonds first. If it fills the octet for everything but hydrogen, then you're done. If it doesn't, then I might have to do a double bond or even a triple bond. So notice down at the bottom. Down at the bottom, it shows that carbon, if given the opportunity, can make 4 single bonds. But on occasion, it may have to share 2 pairs of electrons with another atom, forming a double bond, or it may even have to share 3 pairs of electrons with another atom, which would make a triple bond. So do you see that this one up here is done? Do you see that each hydrogen has 2? Hydrogen will only ever have 2. Hydrogen will only ever have like a single line with it. You'll never have more than 1 line attached to a hydrogen. Carbon has 8, 2 above, 2 below, 2 to the left, 2 to the right. And you can swap out the pairs that are shared with a dash. Interesting thing, carbon doesn't have any non-bonding electrons. Notice that. There's never dots around the carbon because it has 4 electrons. They all participate in a bond. Okay? So carbon, always going to have 4 bonds. Nitrogen, always going to have 3 bonds. Oxygen and sulfur, always going to have 2 bonds. But fluorine, chlorine, bromine, iodine, and hydrogen only ever have 1. Right? So hydrogen is only going to have 1 bond, 1 bond. So that kind of takes out a lot of them. It's really just these. Carbon, always 4 bonds. Nitrogen, 3 bonds. Oxygen, 2 bonds. It's not going to have more. It's not going to have less for our purposes. They actually can, but we're not going to talk about those. Okay? So these are all the possible arrangements. Notice that nitrogen keeps those non-bonding electrons. Notice nitrogen, whether it's 3 single bonds, a double and a single, or a triple, it still has 1 pair of non-bonding electrons. Because remember, that's what nitrogen looked like. Nitrogen had those 2 dots and then 3. That non-bonding pair stays there. Notice with oxygen, the 2 non-bonding pairs stay with it. Sulfur as well. So let's do a couple of these. And here's sort of like the ones that you can do. I've sort of drew this like as a short description. Got kind of long, so then I'm taking up an entire page. So you always list the number of atoms in the formula, list their number of electrons. Remember, the number of bonds equal 8. So whatever their number of electrons plus bonds should always equal 8. Just a way to remember, remind yourself. You always start with the atom that needs the most bonds. That one always gets put down first. Okay? Then add the next atom needing the most bonds, not the number with the most electrons. It's the ones that need the most bonds. So like if I have carbon, nitrogen, and oxygen, I put down carbon first, then I put down a nitrogen, then I put down an oxygen, because one needs 4 bonds, one needs 3 bonds, one needs 2. So I would always list them that way. I keep adding. I always add the atom that needs the most bonds and pair it with the atom I've already put down that still needs the most bonds. You just keep adding until I've added all of them. Once I've placed all of them down, if I don't have stable octets, that is when I have to do multiple bonds. So I might have to do a double bond, or I might have to do a triple bond. You will never have a double bond between fluorine, chlorine, bromine, iodine, or hydrogen and anything. Because remember, they're only ever going to have 1 pair. So only time you're going to have double or triple bonds is if it's between like carbon, nitrogen, oxygen, sulfur, phosphorus. Okay? Those are the only times you're going to end up with more than one bond, because those ones in group 7 only ever form one bond. Hydrogen only ever forms one bond. So you know it's like carbon, nitrogen, oxygen, sulfur. Those are the only ones that are going to possibly form multiple bonds. Okay? So we did CH4. So like in each one, what I would say to do is you write the number of electrons. You can list them out this way, number of bonds. And then always I would start with carbon, add my dots. Then I would add hydrogen, 1 on each. So we already did this one. So look at the one below. So water, the most abundant molecule in the body. Hydrogen, how many electrons? 1 electron, because it's in group 1. That's how I know. Okay, so it's just the group number. So again, you don't have to memorize it. It's the group number. So hydrogen, 1 electron. And how many bonds does hydrogen make? Only ever makes 1. Hydrogen's the oddball. It just needs 1 bond to be stable. But oxygen has how many? It's in group 6. So see in front of the capital A at the top of the column, that tells me how many valence electrons. I got to have 8, so how many bonds? 2, because 6 plus 2 tells me 8. Okay? So the number of electrons plus the number of bonds should equal 8 for everything but hydrogen. So that tells me which do I start with? Oxygen, because oxygen needs the most bonds. So remember that you're going to pair. You're going to have 2 pairs on any side. I don't care which side. You could have 2 on top and 2 on the bottom, 2 on the left, 2 on the right. But the key thing is 2 sides should have 2 electrons. 2 sides should have 1 electron each. And then, because those are the single electrons, that's where I make the bond. So I'm going to now take hydrogen and put it where? At the bottom, okay. And then I'm going to make a pair. And then also on the right, and I'm going to make a pair. So can you see now oxygen looks like it has 8? There's 2 above, 2 below, 2 to the left, 2 to the right. So I can see the 8. Hydrogen only ever has 2. So all I got to do is do 1 pair and hydrogen's done. This is what a water molecule looks like. The dash represents a single pair of electrons that are being shared. So both of those are the same. Notice that I keep the non-bonding electrons that belong just to oxygen. Those 4 electrons that are in the final image, those belong just to oxygen. They don't get shared with hydrogen. NH3. NH3, nitrogen has how many electrons? 5, because it's in group 5. The number in front of the capital A at the top of the column. Hydrogens have 1 each. So that means nitrogen needs how many bonds? 3, because it's got to have 8. So the number of valence electrons plus the number of bonds always are going to equal 8, except for hydrogen. Hydrogen's only ever 1 and 1. So which do you start with? The nitrogen. 1, 2, 3, 4, 5. I put the 5 valence electrons down for the nitrogen. Now I'm going to add the hydrogens, because those are the only ones I have left. So I add a hydrogen here, hydrogen here, hydrogen here, creating a pair between them. I've also seen students write it like this. That's perfectly fine. All I care about is that the dots are between the 2 atoms that are sharing. I don't care if the dots are side by side or if the dots are stacked on top of each other, but they have to be between the nitrogen and the hydrogen. So you can't put the dot. I've seen this too, and this would not be okay. I've seen this. That doesn't look like you're sharing. Okay, that's the hydrogen going mine. Okay, so it can't be on the other side. You got to make sure that the pair that are shared are between those 2 atoms. And I know like the colors, I think the colors like help you to see them, but in your mind, just try to put them down. Start with the nitrogen, give it 5 dots. Then add the hydrogen, add a dot. Some people I see put little X's instead. I don't care about that. Like just something that represents the dot needs to be there. But if the X helps you to think, okay, well, that's hydrogens and this one's nitrogens, that's fine too. Okay? But what about O2? That is how you always have oxygen. If you give anybody oxygen, you're always giving them O2 instead of just O. So oxygen, how many electrons? 6, which means that it's going to have 2 bonds. So in this, they're the exact same. So it doesn't matter which oxygen you start with because they're exactly the same. So I put in oxygen down. 1, 2, 3, 4, 5, 6. And then I've got to add the other oxygen to it. 1, 2, 3, 4, 5, 6. I'll just pair them side by side. Could do them so they're vertical as well. Doesn't matter, just so long as the dots are in between. But you notice now I'm done. I don't have any more atoms and I don't have any more electrons. But does each oxygen have 8? No. If you count, 2 above, 2 to the side, 1 below, 2 between. So that's 7. When you get to this step, this is the last step, and this tells you I'm going to have to make a multiple bond. I'm going to have to move those 2 single dots, the black one and the blue one. I'm going to have to move them between the 2 oxygens to have them shared. So this one and this one, these are going to move. This dot gets moved over here. This dot gets moved here. Once you put them between the 2 oxygens, now they're shared between those 2 oxygens. And now, can you count 8? 4 in between, 2 above, and 2 to the outside for each of them. That's a double bond. So I would use 2 lines instead of just 1 to represent 2 pairs of electrons. So remember that a line represents 2 electrons, 1 from each. What about nitrogen? Nitrogen in the air, 79% of the air in this room is nitrogen. 2 nitrogens, each of them have 5 electrons, which means they each need how many bonds? 3. So you can see right here, it's all I got. It's just 2 nitrogens. So if I start off with 1 nitrogen, 1, 2, 3, 4, 5, and I pair it off with another nitrogen, 1, 2, 3, 4, and 5. Do you see that now I've used all of my electrons? Now I'm going to have to start moving a black electron and a green electron between the 2 nitrogens, creating more shared pairs. So if I move the first group, I'll just move these bottom ones, put a green one, not a line. I'll put a green one right here and move the black one. So I move those bottom ones between the 2. So having them down below, they're not shared. Putting them between the 2 atoms makes them shared. But you see now I only have 7, 4 in between, 2 above, and 1 on the outside. So those ones on the outside also have to move in between. So this black one's going to move in between. This green one's going to move in between. So I'm going to move this one and place them in between as well. Like that. That's a triple bond. You don't see this very much. If you remember in lab, we built one of these and they were all like trying to put the nitrogen and the carbon together. We're pretty tight, but that is a triple bond. And you see 8, 6 in between. So those 6 electrons spend like half their time with each nitrogen, but those 2 electrons on the top, those belong to the nitrogens independently. Okay, so you always start off and just make 1 pair and add. You don't start making double bonds or triple bonds until you've used all the atoms in the formula. Okay, so like in this, it's just N2, so I had no choice. I had to start doing those double bonds and then a triple bond straight away, because once I laid the 2 nitrogens down, that's all I had. Okay, but I would say do double bonds or triple bonds absolutely last. Make sure that you put all your atoms down first, then do multiple bonds if there's no more atoms to add. So like looking at CO2, so going to the other side. So carbon, it has 4 electrons, 6 electrons, 6 electrons for oxygens. And that means that the carbons are going to have 4 bonds for carbon. I was jumping ahead and thinking about oxygen. 4 and 4 makes my 8. 2 and 2 for each oxygen to make its 8. I don't like that green, it's hard to see. 4, 2, and 2. Okay, so which one do I start with? Carbon, because it needs the most bonds. Carbon needs 4 bonds, oxygens only need 2. So I'm going to put my carbon down first. 1, 2, 3, 4. Okay? Put the dots, spread them out. Then I'm going to add an oxygen. I have 2 oxygens left, so they both need the most number of bonds, so I'm going to add the oxygens next. Adding them, 1, 2, 3, 4, 5, and then pair 1. Okay, so I just made a single bond between the oxygen and the carbon. Before I try to do any multiple bonds, add the other oxygen. So make sure you add all of the atoms first. So now I'm going to add this oxygen over here. 1, 2, 3, 4, 5, 6. And there was a question of like, well, how do you know to put the oxygen there? How do you know why don't you put the oxygen on the other oxygen? So if I back up a sec, because I jumped, I started with carbon, it needs the most bonds. I add an oxygen and just create one link. I pair one set of electrons between the carbon and the oxygen. So now I got to add the other oxygen. So do you see that carbon still needs 3 bonds? Do you see that carbon still has like 3 single electrons? So I know carbon still needs 3 bonds, but the oxygen, how many bonds does it need now? How many bonds does the oxygen, the blue oxygen need now? How many electrons does it have? It has 6, but it's formed 1 bond, so now it has, so this has how many? 7, okay? So that means how many bonds does that oxygen still need? 1, okay? So oxygen only needs 1, but do you see that my carbon, if my pen would work, my carbon has 2, 4, 5, okay? So that means my carbon still needs 3 more bonds. That tells me add the oxygen to the carbon. Whenever you add another atom, you're always adding it to the side of the molecule where the atoms still need the most bonds. Does that make sense to everybody? Okay? That's why I put my oxygen on the carbon. Carbon still has 3 empty dots. Oxygen only has 1 that's up there now. That tells me I've got to put my second oxygen on the carbon. So I'm going to set it over here. When I put it over here, would it be wrong if I put it above? No. Or below? No. The kicker is I just need to link it, okay? So my oxygen could be hanging down off the bottom. That would be fine. I just don't have that much room, okay? So I'm just putting them this way. It could be sticking up off the top. The kicker is the carbon needs to be attached to the oxygen, sharing a covalent bond, and then I put another oxygen and share a covalent bond with the carbon as well. So I'm done. I've used my 1 carbon and my 2 oxygens. Do you see all these empty dots, right? Do you see these dots that are not paired? The ones that are not paired, now I have to form double bonds. So the first double bond is I'm going to move the single red dot, the left oxygen has an unpaired, see this one? I'm going to move that one in between the carbon and oxygen, and I'm going to move this one between the carbon and the oxygen. So I'm going to move those so that it forms a double bond. Moving this one, putting it here, putting this one here. Now, the red oxygen, how many electrons are around the red oxygen? 8. Do you see 8? So there's 4 between the red oxygen and the purple carbon. There's 2 above and 2 to the left. So that's 8. So that oxygen's done. Okay? But look at the blue oxygen. The blue oxygen has how many? 7, because there's that 1 dot underneath that doesn't have a pair. Carbon still has 1 dot above that doesn't have a pair. So this one and this one, they need to move between the carbon and the oxygen. And I don't have to put them between the red oxygen because the red oxygen has 8, so it's done. But the blue oxygen is the one that doesn't have an 8, an octet. So I need to pair the single electrons of the carbon and that blue oxygen, moving them in between. So this one moves and this one moves. So now I got a dot here and I got a dot here. Can you see that now carbon has 4 on either side? That makes 8. Oxygen has 4 between and then 2 and 2. That makes 8. So I had to put my carbon a double dash to the oxygen to pair them. Oop, I gotta stop. Okay, that's carbon dioxide. Carbon dioxide has 2 double bonds